Okay, so I think we can start. Okay,
Thank you.
Welcome everybody for being here today with AJS. Today, it's a pleasure to present the speaker, Nicola Clinco. He's a first-year PhD student in the MATLAB group, and he will talk about filter stabilization for the compressible Euler equations with application to atmospheric dynamics. So, Nicola, the stage is yours.
Thank you. First of all, I know that it is a long title, but I will resume that in a filter stabilization for weak incompressible flows, okay, with emphasis in atmospheric fluid dynamics. So the overview, we will cover the following arguments. We will see briefly what are the motivations, what has pushed me in doing this research. Then we will see what is the central part of the work, that is, what is the evolved filter relax algorithm. Then we will move on the central part of the work, that is, what is a filter in our case, what is a filter stabilization. And at the end, we'll see some results and findings, some peaks, pictures, and so on. And at the end, I wanted to add another work that I'm currently doing, that is the development of a fully explicit density-based solver for the atmosphere. Okay. We are interested in the numerical resolution of this set of equations that is the compressible Euler set of equations in the presence of gravity terms. In particular, these equations are used in the atmospherical flows dynamic simulation when the spatial scales are tens of kilometers. Yes. What is the main problem? The main problem is that there are long time intervals to be simulated, and so we need a certain trade-off between the accuracy and the computational cost. Okay, and for this reason, I'm proposing a modular algorithm that is called evolved filter relax. Okay, in order to understand better what I'm saying, imagine that you want to do your simulations, yes, and since the spatial scales are 10 kilometers, range about tens of kilometers, you are not able to simulate all the possible scales. Indeed, you need a really fine grid, and you need a huge number of degrees of freedom. Why? Because we need the mesh spacing, or the distance between the degrees of freedoms, has to be comparable to the so-called Kolmogorov scale. That is the smallest eddy that you can have in your simulation. Before that someone fires me in the audience, I will say that this formula, so the Kolmogorov scale, okay, is referred for homogeneous turbulence, but it's just to give an overview, nothing more. Okay. So the first bottleneck is the grid requirement for doing for simulate all the scales. We need a really fine grid, and we can't, because for a finite volume approach in 2D, we need 10 to 16 cells. Okay. Not only the storage, but also the fact that in order to maintain a certain stability, that is, in order to respect the CFL condition, we need a really tiny time step. And so we need, nowadays, we are forced to adopt a coarse mesh. Okay. But if we adopt a coarse mesh, the things are bad. Indeed, we'll see this test case later, that is a cold bubble that touched the ground, and then some vortexes are developed. But we need a certain stabilization. Indeed, we need to take to cut the smallest eddies, and we need to cut the high frequencies. Okay. The way we do that in the following manner. the evolved filter relax algorithm is consists in 3 big blocks. The evolved step. In the evolved step, we just solve the equations that I cited before, the Euler equations, with theoretically with whatever solver we want. At least it must work. And in our case, since the velocities are small, we have adopted a generalization of the pressure implicit with the splitting of operator, but adopted for the weakly compressible flows. And the space discretization is a second order finite volume, a collocated second order finite volume with a centered scheme, a fifth order centered scheme. Okay, so at the end of this step, we just obtain the density, the velocity, and the energy, but in my case, I have chosen the enthalpy. Okay, the second step that is the crucial, okay, is the filter step. That is, in my case, nothing more the application of a differential filter. Indeed, we take the high frequency content in the solution and we cut them, nothing more. The third step instead is a linear combination between the solution at the end of the evolve and the filter step. And it was introduced in the literature in order to avoid overdiffusion. Okay. But at the end, in my work, I have omitted the relaxation step because at the end we have just shifting the problem when we must tune some parameters, as we can say, we can solve later. But if we retain the relax step, we just shift the problem in order to shift the problem of the parameters because we cannot able to understand these parameters at the moment. So I have omitted. Okay, if we put everything together, all the complete algorithm, it corresponds to perturb the momentum and the energy equation. Indeed, there are some red terms that are bad and ugly, and green-blue terms that are the terms that help us to stabilize at the end. However, the red terms are small. At least I have shown in the bottom, there are 2 panels that show the order of magnitude of the red terms that are terms that comes from the splitting error. And indeed, both for the velocity and the enthalpy, they are smaller respect to physical quantities that we are simulating. Indeed, for the velocity, we have 0.02, and for the enthalpy 10, but the enthalpy is 10 to power 5 joule or kilogram of Kelvin, so there are no problem. However, the interesting thing, the most important thing is the presence of the green term, because they help us to stabilize. Okay, indeed, the green terms are nothing more than can be thought as an artificial viscosity model. In particular, here we can understand the connection with a explicit subgrid scale model. Indeed, alpha square A divided by delta T is nothing more of an artificial viscosity. Okay, kinematic viscosity. I know that I have used nu for alpha square A, but nu is just a symbol. Okay, the kinematic viscosity is alpha square A divided by 1 delta T. Okay. Okay, but the central part of my work is the filter step. The filter step is, as I said before, is a differential filter, nothing more. And so we at the end solved a weakly nonlinear evolved problem. Nonlinear because AQ is a scalar function, nonlinear scalar function, as we'll see, and has the main role to stabilize and to detect where there is shear flow in our simulation. While alpha is the filtering radius that tells us how big we are averaging our variables.
Nicola, just go to the previous page once.
Yes.
Where is this connection with an explicit SGS model? Have you borrowed anything from this idea in your code, in your algorithm?
Yes. Yes.
Which part?
In-
You
in
have
what
borrowed from SGS model.
Okay.
Which part of the algorithm
Okay.
is borrowed from the SGS model?
Before the green part.
Okay, so this is part of your filtering process.
This is the complete process. Evolve, filter, relax.
Yeah, so that green part came from what? Filtering part?
Yeah, okay. Okay, I understood. If the filtering part, but it is difficult to say from where it comes from, because if you do all the calculations, they are wrong. And if you glue together the relax and the filter and the relax step, you retain all the terms.
Okay, it's not something is coming from water.
No, because the Xi and key are the relaxation parameters. Okay. In my case, Xi and key is equal to 1 because everything is filtered.
Yeah, but your filtering equation is the next page, the one you are showing now.
Yes.
That indicator function.
Okay, we will test 3 types of indicator function that are the linear, the gradient type, let's call that, and the convolution based. That are the 3 most well established in the incompressible flows. Okay, the linear type is equal to 1, is a Dine scalar function that is equal to 1, so it regularizes everywhere. The gradient type is a sort of normalization of the gradient of the velocity, and the convolution based is more involved because you need to solve an intermediate step in which you filter the solution, the velocity at the end of the evolve, and obtain overline 2, that is an intermediate velocity. And then you use this velocity to evaluate the difference between the unfiltered velocity again, v, minus an approximation of the inverse of filtering. V, indeed, it is an approximation of f at the end. And it is the first iteration of the Van Kittert operator, Van Kittert algorithm, or the operator. And in my case, since n is equal to 0, is nothing more than the identity. Okay. What is the main bottleneck in all of together? That we have not a suitable strategy to tune the alpha, the filtering radius for the convolution based. While for the linear type and gradient type, we are able to tune that by connecting them to the standard turbulence models, at least for the gradient type. Indeed, for the gradient type, let's see the last panel. For the gradient type, we are able to, we request that in every degree of freedom, we inject the same viscosity of the standard Smagorinski. And thus we can tune alpha for the gradient type. The same happen, however, for the linear, by requiring that we inject the same viscosity of an equivalent artificial viscosity model, nothing more. The bottleneck is the convolution based. We have not a practical way to tune the filtering radius. And for this reason, we'll set the filtering radius heuristically by we just require that we just need to tune alpha as Smagorinski, as the gradient. Indeed, we adopt a filtering radius of the same order of magnitude of the gradient at the end, and we compare the result. Okay, the filter step could be seen and could be theoretically generalized to a Stokes problem. If we divide the filter step by delta t, we obtain a sort of Stokes problem. And so in the literature, it is done in the incompressible case. You can adopt another time-stepping scheme, and you can generalize this equation at the end. However, in our case, a BDF1, we have adopted a BDF1 for the root step, and so we are happy with BDF1. Okay, some results. The first result is the rising thermal bubble. It consists in a time evolution of a circular bubble that is warmer than the environment and it. So as the simulation, as the time passed, the circular bubble evolves, and at the end we obtain a sort of mushroom. Okay. Now, one thing that I will say that the results are shown in terms of potential temperature. That is a physical quantity that that tells us about the stability of the atmosphere, and for this reason, the meteorologists are interested in using these variables as post-processing. Okay, these are the results for the linear, and these are the results for the nonlinear models, the gradient type and the convolution based. Not from the top panels, that the convolution based is more selective. Indeed, the Kelvin-Helmholtz instabilities are triggered well by the convolution base, while the Smagorinsky just cuts everything, okay? Especially for the 31.25 meters mesh. Yeah. Okay, the test that I will analyze better is this one, is the density current benchmark. Density current benchmark is the dual than before, and at this time, the bubble is elliptic and is colder than environment and surround it. Thus, thanks to the buoyancy, the bubble will travel to the bottom, will hit the ground, and then a sort of vortexes are developed during the time evolutions. These are the results for the linear. We have tuned again the alpha radius in such a way we have the same artificial diffusion of of 75 Pascal per second. And these are the results compared with an higher order schemes. In the dashed line is obtained with a discontinuous Galerkin scheme 7th order. And we know that the curves are, for all the meshes, the curves are shifted to the right. I think that it is not due to the space discretization. Why? Because we will see that later. Don't worry. We'll see that later. Okay, a little bit of color fluid dynamics. These are the results of the gradient type and the convolution based for the finest mesh that we have tried. The results are different, despite the filtering radius are the same order of magnitude. Okay, this is the video that we cannot open. No. Yeah. Okay, we can see clearly what are the differences. Oh, okay, we have not said nothing. We can see the differences between the convolution based and the gradient type. The convolution based detect locally what happens, while the gradient type, okay, is expired. Sorry, again. Okay, the gradient type instead smooth, not everything, okay, but is more is less local respect the convolution base. Okay, despite the locality of the convolution base, if we adopt a filtering radius of the same order or the same order of magnitude, we know that the space average viscosity for the two nonlinear models are perfectly comparable in magnitude. Indeed, we note that the time evolution are similar for the same mesh size. Okay, this is quite interesting. Okay, this is another video that resume this everything. Oh. Okay, this video resume everything because okay, one thing. Oh no.
Just stop.
Sì, just stop.
Meno spaziatrice non mi viene.
Okay. Undefined. No, just see the detail undefined at the final time. Okay. One more. Okay. The linear type is the most dissipative. Indeed, the solution is smooth enough. While the convolution based is again local, is a local filter. Indeed, the differences are qualitatively well seen in the biggest rotor at the end of the bubble. Okay, and this assume at least what happened. Put the full. Okay, for this work, I would assume that the linear filter is the most dissipative, while the convolution based is the most selective, as we have seen. There is a future. There is the bottleneck. The main bottleneck is that we have not a practical manner to tune the filtering radius for the convolution based, and also the relaxation parameter. And this is the main bottleneck of the approach. But at least all the standard turbulence models have this bottleneck for the constant. Okay, if you take the Smagorinsky constant, for example, they are adapted simulation by simulation. Then it could be interesting to apply the evolved filter relax algorithm with other solvers, okay, other space discretization. And at the end, it could be interesting to investigate other type of indicator functions based on physical quantities. Okay. This concludes my master thesis work. But I want just to give a brief overview on another work that I'm currently doing. That is not the continuation before, but the application is the same. We are still in the mesoscale modeling in atmospheric flows, but the focus is different. Indeed, in this case, I'm developing a fully explicit density-based solver with finite volume in a finite volume approach collocated in the presence of the gravity and okay, the bottleneck here is the treatment of the source terms. Why? Because in the before, yes, one thing that I have not said is that in my master thesis, the well-balanced property of the scheme was ensured by an elliptic equation for the pressure. Indeed, the scheme was well balanced by requiring that the elliptic equation for the pressure is well balanced. Okay, in this case, the solver is fully explicit, and for this reason, if we adopt a standard finite volume discretization, the things are bad. Why? Because if we start with an atmosphere at rest, okay, so we have a constant potential temperature. With a flat terrain, we expect that the velocity, the vertical velocity, has to be 0 in the time. But it is not the case, because the velocity after 60 seconds, the velocity reached 900 meters per second. Why? Because the source term is bad and ugly. Indeed, in this sort of thing, the thing that is done is to treat the source term in a proper way. And in order to do that, we split the pressure and the term and density in an hydrostatic state and in an hydrostatic term and a perturbation term. For the hydrostatic term, the Savino laws is valid. And if we use the Savino laws in the finite volume approach, we can discretize the source term in the following manner, and we can put it in the equation. And at this time, theoretically, the left-hand side term, that is pH, that is the hydrostatic term in the flux term, balance perfectly the source term. At this point, someone can say, okay, you can simplify pH. Well, you can't. You can't do that because in the density-based solvers, we solve the Riemann. In order to solve the Riemann problem at each interface, we need the total pressure. And for this reason, at each time step, we must reconstruct this term from the cell center to the surfaces, because we are adopting a collogated volume approach. How can we reconstruct at each time step the pressure, the hydrostatic pressure? I forget that, but here is pH. Okay, or I'm referring to an hydrostatic state. And okay, for each time step, we must reconstruct the pressure at each cell interfaces. And if we use the original equation, we obtain an ugly nonlinear system. And since we want to avoid weakened lack of robustness by doing that, basically we can just solve this one with an iterative procedure. Okay, but recall that we must have available the vertical gradient of the potential temperature that comes from the energy equation. And so we have problem of robustness. However, in my case, since we have an homeotropic atmosphere, we can discretize, we can obtain we have analytical formulas to extrapolate the density and the pressure at the surfaces. So at each time step, at the end, we can just obtain the density and the pressure from the center to the faces thanks to this equation. For P prime, instead, I have omitted the details. We obtain an ad hoc reconstruction conceived for the evolution of perturbation. It's not the reconstruction of the standard finite volume. I have omitted the details just.
And what flux, like that convective flux discretization scheme you used?
It depends. Rho, HLC, Hausm. I have compared different
cases. Oh, okay.
As I will show now.
Oh, cool.
Indeed, for the this is a test case that tests the well-balancing property of the scheme, and indeed we obtained 10 to -9 meters per second. So for the Rho and HLL schemes, that are schemes that are not conceived properly for the low Mach number flow. And indeed, if we adopt other types of schemes, the things are not will not achieve 10 to -9 because the numerical dissipation plays a fundamental role in this. And indeed, if we do the density current benchmark for different schemes, we have different results. The HLLC Hausm that are conceived for the weakly compressible flows are able to trigger the perturbations, while the HLLC and Rho are more dissipative, as you can see. Before I said that the shifting is not due to the space discretization. Why? This explains everything. I know that someone can say that the shifting could be due to different set of equation, because here we are solving the total energy and before the enthalpy. But I think that the shifting was given by the fact that we were using a temporal scheme that is first order. In the literature, is not well established why it is, but I have read two articles that, and it could be, in my opinion, the shifting was attributed to temporal scheme. In my opinion. However, with the fully explicit density based solver, we obtain results that are almost overlapped with an higher order scheme. Okay, and this is just an overview of my last work that Nicola was doing. Okay. Thank you to all for questions.
Thank you, Nicola, for the nice talk. So, time for questions. Are there any questions here in presence?
Okay. Well, why did you go for compressor flow solver for such low Mach number flow? Can you approximate incompressible flow with some Gaussian approximation or something?
Yes, the results change. If you adopt an incompressible flow, if you retain that rho is constant, you don't obtain these results.
Okay. So
it's strange, but
yeah, I know this kind of solver sucks at the low Mach number regime.
Okay. Yes. The fact it is just a comparison, because in the literature it was never done, and so I thought that it could be interesting.
You can actually modify those solver a bit to work in the low Mach regime. Yes. And one more question is that do you think that that improvement of that indicator function will improvement the resolutions? Like any further research is required in improvement of indicator function? You don't know.
The fact is that I have just linked, if you take, for example, the gradient type, I have linked all the parameters to standard turbulence models.
Oh, okay.
I think that the word improving in the turbulence is not quite straightforward, because there are many parameters to do. And improving, I don't know how can we can achieve that. That's that. Maybe there are other types of indicator function based on the Q criterion or the vorticity, helicity, but I have tested only these three, so because they are robust and they.
Yeah.
So.
I mean, I'm saying that if we want to improve my result, which factor I should look at first? Indicator function or some filtering radius? Which one?
Indicator function.
Okay. Thanks.
If you want to do the.
I mean, I want to keep my same course mesh size, but I want a better result. So then function. Okay.
Indicator function.
Okay. Thanks.
Okay. Any other questions? Yeah. Maybe I have a curiosity on the filtering radius. You said that it's difficult to tune the filtering radius somehow.
Yes.
And how did you tune it?
Depends. For the gradient type here, for the gradient, I have required that in every single degree, not in every single degree of it, I have required that we inject almost the same diffusion of the standard Smagorinsky model. Indeed, this
is a formula basically.
Okay, this is the formula for the Smagorinsky. Okay, I have approximated the double scalar product of the strain by the gradient. Okay, the L infinity norm of the gradient, and then I have connected a this formula that is the normalized gradient with this one. So the gradient here simplified with this one, and we obtain alpha for the gradient. For the linear, we do the same thing by requiring that rho alpha squared delta TA is equal to an artificial viscosity that is chosen by others in the literature.
Okay.
For the combustion based, we are not able to at the moment to estimate the.
And have you tried like a sensitivity analysis for this parameter? So like different also random parameters and see how it works.
Yes, yeah, for the combustion based, yes.
Okay.
For the combustion based, we have indeed. If you look carefully at the pictures, okay. If you look, for example, this video in the gradient type, I have fixed alpha to 11,
Okay.
and the conversion base 12, I have augmented slightly.
Because you saw that maybe it was better.
Yes.
Okay, maybe, I don't know, maybe you can try with machine learning techniques also to tune. It's what I'm trying actually in my project. So it can be useful. Maybe.
For alpha or for the relaxation parameter?
For both. I mean,
because we are shifting the problem. So
yeah, if you do just EF, you can do this just for the filtering parameter.
Okay.
So any other questions from the online part? If yes, just unmute yourself. No? Okay, so I think we can finish here. Let's thank again the speaker, Nicola. And see you at the next AJS. Thank you.